Welcome to the lecture series on alkyl halides. This is the last episode of alkyl halides, and in the previous episodes of alkyl halides we have covered the structure of alkyl halides, the nomenclature, preparation and physical properties, the reactions, and in the previous episode we started with aryl halides. And in aryl halides we talked about the structure, the nomenclature, the preparation and physical properties. In the present lecture we shall start with the reactions of aryl halides. The reactions can take place at the benzene nucleus, and the types of reactions include electrophilic substitution reactions, the nucleophilic substitution reactions, and also the reactions at the aryl side chain. The reactions at the aryl side chain would include the SN2 and SN1 type, which we covered while studying the substitution reactions of alkyl halides. The aryl halide reactions. Aryl halides exhibit the following types of reactions depending on the structure of halide and the reaction conditions. The reactions can be electrophilic, nucleophilic, nuclear substitution, the nucleophilic nuclear substitution, or the nucleophilic side chain substitution. As we proceed in the lecture, we will understand the meaning of these terms. We shall start with the basic structure of aryl halides first. Aryl halides may have halogen atom bonded directly to the ring. The halogen atom is attached to the double bonded sp2 carbon, so it is strongly bonded to the carbon and therefore is less reactive. This is one way we have aryl halides. This is chlorobenzene and similarly another homologue 1-bromo-naphthalene. When the halogen atom is not bonded directly to the ring, then we have a molecule, we call it as benzyl, and the structure and properties of these halides are similar to the ones we observe in case of alkyl halides. One of the examples is benzyl chloride, and as can be seen here, the halogen atom is not directly attached to benzene, but it is attached to this methylene group. The aryl halides undergo electrophilic substitution at the benzene nucleus, and they are reactive towards electrophilic substitution like nitration, sulfonation, etc., but these are less reactive than benzene. The halogen atom is electronegative and has a tendency to withdraw electrons from the benzene nucleus towards itself inductively through the sigma bond, therefore it is deactivating. No doubt these arenes also undergo electrophilic substitution reactions. The halogens have lone pair of electrons on them that can donate electron density through pi bonding. Therefore, these are ortho and para directors and deactivators to meta position. If we look into this reaction, chlorobenzene undergoes nitration and produces three types of products. One is ortho, another meta and para. The percentages are that para, being the least sterically hindered, gives maximum amount of the product, whereas the next is ortho product, which is obtained in 35% of amount, and meta product is hardly obtained. The attack at the ortho or para position generates a sigma complex that can put the positive charge adjacent to the halogen substituent. We can see in this structure there is a positive charge and chlorine is directly attached to this particular carbon atom. The directing effect of halogen atoms in aryl halides is due to the resonance stabilization of this cationic intermediate. In case of para attack, the lone pair of halogens is released to stabilize the positive ion intermediate. The positive ion intermediate shows a number of resonating structures, and there is extra stabilization due to the lone pair of halogen atom. These resonating structures stabilize the cationic intermediate. Similar to para-ortho substituted anionic intermediates has an extra structure stabilization. So, this particular ion also gets stabilized. This is an ortho substituent where again the lone pair on chlorine atom helps in the stabilization of the intermediate, and we get a double bond during the resonance stabilization. The meta substituted intermediate does not have a stabilization like that of ortho or para. As we see in these resonating structures, the positive charge keeps moving over the benzene ring, but it is not shared by the chlorine atom. Therefore, the meta substituted products are not stable. Substitution of the halogen atom by a nucleophile, as in the case of alkyl halides, takes place, and we call it as substitution nucleophilic aromatic. It is represented by SNAR. In case of aryl halides, the substitution is at sp2 carbon. So, the halogen group halogen atom is attached to this sp2 carbon. The nucleophile attacks this carbon and replaces the halogen atom. But the aryl halides do not exhibit the SN1 and SN2 types of mechanisms what we observed in case of alkyl halides. The halogen atom bonded to a sp2 carbon makes the CX bond stronger and less liable to attack. So, if we notice that in presence of sodium methoxide, the bromobenzene does not show any substitution. The CX bond actually has a partial double bond character that makes it unavailable for substitution. The lone pairs on the halogen atom participate in the resonating structures and give it a double bond character. As a result, the substitution becomes very difficult. Therefore, we observe other mechanisms for substitution reactions in aryl halides. The nuclear nucleophilic substituted reaction may take place under two conditions. So, one is when the aryl halides have electron withdrawing groups at ortho or para position like nitro group, cyanide, sulfonic or carboxylic group. So, in presence of nitro group as the electron withdrawing group, we see that under some rigorous conditions there is substitution by hydroxy group and formation of the substituted product. The substitution may also take place if the nucleophile is very strong. If we use potassium amide as the nucleophile, where it has NH2 group as the nucleophile, we see that the substitution takes place. We get the formation of aniline. If we look into these reactions where we have one nitro group as the substituent and in the other we have two nitro groups and then there are three nitro groups, it is observed that if there is only one electron withdrawing group like nitro, then under very rigorous conditions and a high temperature we get the substituted product, whereas in presence of two nitro groups the conditions get milder. Instead of a strong base, sodium carbonate, a milder base can be used and we can get a substituted product. In case of the presence of three nitro groups, this chlorine atom can be easily replaced by hydroxy just by warming it in solvent water. The mechanism of nucleophilic substitutions, as was said earlier, it cannot undergo an SN2 type of mechanism because it cannot provide a suitable geometry for backside attack of the nucleophile. The aryl ring blocks the attack of the nucleophile. Therefore, the aryl halides do not show SN2 mechanism. Aryl halides do not show the SN1 mechanism also, as the ionization of a aryl halogen bond to give an aryl cation is difficult to achieve. So, there are other mechanisms for nucleophilic substitution reactions in alkyl halides. There are two types. One is addition elimination mechanism and the other is elimination addition mechanism. Let us look into these two mechanisms in detail. The addition elimination mechanism of nucleophilic substitution in aryl halides is when the nucleophile adds first and then the leaving group is lost. So, in this case we are using nitrohalobenzene, which is attacked by this methoxide first, that is the addition is the first stage, which gives rise to an anion. This is cyclohexadienyl anion, which in the second step, which is a faster step, undergoes elimination and gives rise to the substituted product. The first step, being the slower one, is the rate determining step. So, let us look into these steps in detail. The first step is addition of nucleophile to give an anionic intermediate. This anionic intermediate is called Mesenheimer complex. This is the hydroxide ion, which is the nucleophile. It attacks the carbon which is bearing this halogen atom and gives rise to this Mesenheimer complex, the anion, and this anion is actually in the resonating state. The negative charge on the anion is delocalized over the whole ring. As a result, it is quite stable, and this is the resonance hybrid of this particular structure. In the second step of this mechanism, elimination of the halide ion from the Mesenheimer complex takes place and the product is resulted. And at this stage, the aromaticity which was lost in the previous step is also restored and we get hydroxy substituted nitrobenzene. There are number of evidences to the addition elimination mechanism. First of all, the kinetics. The rate determining step involves both the substrate and the nucleophile, and hence it is a second order reaction. And effect of groups in the ring which has been observed, which substantiates this mechanism. It has been observed that electron withdrawing groups present in ortho and para position help in stabilizing the anionic intermediate. Stabilization of the intermediate is not possible in case of meta substituents. So, when there is an ortho or a para substituent like this nitro group, which is electron withdrawing, and in the first stage addition of the nucleophile has already taken place, this anion is stabilized by the nitro group, which is able to share this negative charge. As a result, the intermediate is quite stable. In case of meta substituent, there is no possibility because this negative ion is formed at different positions in the benzene ring. As a result, the nitro group is not able to contribute to the sharing of this negative charge. The negative charge is shared only among the ring carbon atoms and not by the substituent. Therefore, it is not stable. The leaving groups also show some effect on these reactions, and it has been observed that fluoride shows highest reactivity. And if you recall what we did in case of alkyl halides, fluorides happened to be the least reactive. It's because the more electronegative the group, the greater is the ability to attract electrons, which increases the stabilization of the cyclohexadienyl anion. And as you can see here, the more electronegative group here will be able to share this negative charge and hence lead to the stabilization, and therefore, the order of reactivity in case of aryl halides is that aryl fluoride is most reactive, whereas aryl iodide is the least reactive. The second mechanism of nucleophilic substitution is elimination addition mechanism, wherein the loss of leaving group is taken up first and then addition of nucleophile takes place. This mechanism is followed when the nucleophile is an exceptionally strong base like an amide ion. The reaction takes place even in the absence of electron withdrawing substituents. So, chlorobenzene reacts with potassium amide in liquid ammonia to give aniline by this mechanism, and this mechanism is also called as benzyne mechanism, because in the first step removal of hydrogen halide to form a benzyne intermediate takes place. The intermediate has a triple bond formed by the sideways overlap of the two sp2 orbitals. This is the structure of a benzyne molecule. As you can see, the three double bonds are intact. Besides that, there is another bond which gets formed. This triple bond gives rise to the structure of benzyne molecule. The benzyne intermediate is a very reactive species. A normal triple bond has two sp hybridized carbons, and the atoms attached to these carbons are linear because the bond angles are at 180 degrees. But the triple bond in benzyne is not a true triple bond, and the original double bond is unchanged in benzyne. The extra bond results from the overlap of sp2 orbitals on adjacent carbon atoms of the ring. So, looking at the structure of benzyne intermediate, we see that the axis of the sp2 orbitals are in the same plane as that of the ring. Therefore, they cannot overlap with the pi orbitals of the aromatic system. Consequently, there is little or no interference with the aromatic system. The additional bond is very weak and the benzyne is highly unstable, therefore, it is very reactive. So, look into the elimination addition mechanism in detail. The first step involves elimination, which again takes place in two steps. In the first step, first the abstraction of hydrogen by a very strong base like NH2 to form ammonia and a carbanion takes place, and the negative charge which is obtained at this stage is localized. It is not moving over the ring. At the second stage of the first step, loss of halide anion is there and formation of the benzyne molecule. The second step also has two stages. In the first stage, addition of amide to form a new carbanion. So, this is benzyne. Since there are two positions where this amide ion can attack, this amide nucleophile either attacks here and gives this anion, or there is another possibility that the amide ion, the nucleophile, can attack the other side of the benzyne, which is a symmetrical structure, and give rise to another product. In the second stage of second step, addition of a proton from an acid or ammonia leads to the neutral compound. So, in presence of ammonia, this anion abstracts another proton, gives the neutral aromatic aniline, and the amide ion is regained here. The existence of benzyne intermediate can be substantiated by isotopic labeling experiment, which was done by Robert and co-workers. The carbon atom bearing chlorine in chlorobenzene was labeled with the isotope of carbon, that is 14C. The labeled compound was reacted with potassium amide in liquid ammonia. It was observed that the product was a mixture of two types of anilines. In one, the amide group was found to be attached to labeled carbon, while in the other, the substituent was found to be bonded to the unlabeled carbon. So, this is the labeled chlorobenzene, and it reacts with amide ion to give rise to aniline, which is attached to unlabeled carbon as well as to the one attached to the labeled carbon. Thus, benzene exhibits sign substitution, that is, substitution at a position which is different from the one which was occupied by the leaving group. So, this is the leaving group which was attached to this labeled carbon, but we have a product where the carbon is not labeled. Another evidence to benzene intermediate existence is when there is a substituent at ortho position of aryl halide. It is observed that the product is a mixture of ortho and meta substituted compounds. This is bromotoluene, which undergoes nucleophilic substitution, forms a benzene intermediate which is symmetrical in nature, and by attack at ortho we get ortho amino toluene and also the meta product. When there is a substituent at para position, the product is a mixture of para and meta substituted compounds. So, this is para-chlorotoluene. In presence of sodium amide, it gives again a para and a meta substituted product. Now, the existence of benzene can be understood if we consider this para substituted bromobenzene, which undergoes the nucleophilic substitution by virtue of formation of a benzene intermediate. The benzene intermediate which is formed here is symmetrical in nature, can be attacked at this position or the position which is meta to this methyl group. By attack at the para position, we get para-toluidine, whereas the attack at the meta position gives rise to meta-toluidine. When there are two substituents present ortho to the halogen substituent, there is no reaction due to the absence of hydrogen ortho to halogen. So, we see that this bromo compound has two substituents and both of these are substituted at ortho position. At one position we have methoxy group and at the other one we have methyl group. There is no hydrogen available which will give rise to the formation of benzene intermediate. Therefore, such aryl halides will not show the nucleophilic substitution. Aryl halides react with metals as the alkyl halides, and when they react with magnesium metal, formation of Grignard reagent takes place. So, aryl halides react with magnesium in dry ether to form aryl magnesium bromide. The halide activity goes in this order, that iodide is the most reactive and chloride is the least one. Bromobenzene reacts with magnesium in ether and forms phenyl magnesium bromide. Aryl lithium compounds are obtained on treatment with lithium. Iodobenzene reacts with lithium metal and gives phenyl lithium. Nucleophilic substitution can be shown by aryl halides when it takes place at the side chain. And as we saw in the first two slides, the side chain halides which have benzene ring are called as benzyl halides. The nucleophilic substitution in benzyl halides show better reactivity as compared to allylic and alkyl halides. The SN1 in case of benzyl halides requires ionization of the substrate to generate the carbocation, and benzylic cations are resonance stabilized, therefore, they undergo reactions very easily. So, this is benzyl bromide which loses the bromide and gives this cation, as we saw in the case of alkyl halides. This positive ion gets stabilized by the resonating structures which are due to the presence of this benzene ring. If a benzylic cation has more than one phenyl group as a substituent, then the stabilizing effects are additive and they lead to extra stability. For example, triphenyl methyl tetrafluoroborate salt is a stable ionic solid. So, generally we do not find the intermediates to be separable or as the solid moieties, but this particular cation is highly this particular complex rather is very stable. The SN2 reactions in case of benzyl halides are 100 times faster than the primary alkyl halides. The p orbital that partially bonds to the nucleophile and leaving group also overlaps with the p electrons of the aromatic ring, and this kind of conjugation lowers the energy of the transition state in case of SN2 reactions. You would remember that there is a backside attack and the nucleophile as well as the leaving group remain partially bonded to the halide in the transition state. The transition state in case of aryl halides is highly stable. The SN2 reactions of benzyl halides are good methods for converting aromatic methyl groups into different functional groups via halogenation followed by SN2 substitutions. So, these have a lot of synthetic value. This is para-nitrotoluene, which on halogenation gives para-nitrobenzyl bromide, which in presence of sodium methoxide undergoes a nucleophilic substitution and gives rise to this ether. Similarly, this is orthobromotoluene, which is halogenated to get the alkyl bromo product, and in presence of sodium cyanide it gives cyanide substituted in this particular alkyl group and the bromo compound. So, this is all about the alkyl halides and aryl halides, their reactions, their properties, the structure, the preparation. With this, we finish our lecture series on alkyl halides, and in this particular lecture, let us sum up what we have taken up. We have taken up the reactions of aryl halides, and the aryl halide reactions can be categorized into the reactions at the benzene nucleus, which was covered under electrophilic substitution and nucleophilic substitution reactions, and the reactions of aryl halides include the reactions at the aryl side chain also, and we saw that how these resemble the SN2 and SN1 type of reactions in alkyl halides. Thank you.